What's up, everyone? It's Calc Time with Miss Wesley. So excited to be here today. And our topic for today is still using integrals to find area between two curves. But here's what switches up. Whereas before, maybe we had a function that bounds a region from the top, another function that bounds a region from the bottom, and we were interested in using an integral to find the area between the two. We would integrate top function minus bottom function in terms of our expression. But today, what would happen if those two functions intersect each other more than 2 times? It's possible for the functions to crisscross, and maybe another function could be considered the top and the other the bottom. So we're going to start up with the examples that we see on page 5 of your area packet. So while you're getting yourself set up to take notes with me and try these examples, I like to start things with a joke. And this particular joke is mathematical. You have these 2 4s. So why did the 2 4s not go down to the cafeteria for lunch? And that's because the 2 4s, they already ate, because if you add them up, you would get 8. So feel free to use that joke on your friends and family. We want to give this one a try. So we have these 2 functions. I'm looking at f of x and g of x, trying to get an idea of a rough picture so that we could sketch the region or regions in question. And we could always use technology to help us out with this too. So before I use my calculator, let me just envision what these things look like. You've got f of x is a cubic function with a positive leading coefficient, some kind of S-curve oriented upward. And then you've got g of x is a second degree function, it's a quadratic, and I've got that negative leading coefficient that causes it to open down. So I went in and just to get an idea of what these things looked like, I tried to sketch them, graph them in my calculator, and I got what we suspected, the blue function that is an S-curve, and then the red one that's the upside down parabola. But especially, let me zoom this in, I'm noticing I see 2 different bounded regions, and you can't always say that the red function bounds from the top, nor does the blue. They crisscross, so we're gonna have to set this up in 2 separate parts. So I'm going to try my best to give a rough sketch of this. So you've got the S-curve, looks like it goes straight through the origin. You've got, please don't make fun of me for this picture. Please spare me. This will be the quadratic that looks roughly like that. Not my best work. This is g of x. And then the function that was the S-curve that was called f of x. And I could shade 2 different bounded regions in question. And this is what our goal is, to find the total area of this lavender region here. And then could I also, let me switch to blue, this blue region here. And I feel like this is our dilemma, that we can't always call one of these 2 functions the top or the bottom. We're gonna have to split this into 2 parts. Calculators and Desmos can help me find those intersection points just in case. It's always good to go back over the easy algebraic steps you can use to get intersection points of these 2 functions. And it would be really nice to be confident in these 3 x values that you see here where the functions cross. So don't forget, this is like solving a system. You want to know where these 2 functions are going to equal one another. So why don't we set their expressions equal to one another. So 3x cubed minus x squared minus 10x set equal to negative x squared plus 2x, right? The beauty of a video like this is I tend to talk quickly, so you are able to pause me, you can rewind, you can slow me down. You can also pause right here, try to do the algebra yourself. Try to get everything to one side of the equation and then see if you can factor to find the intersection points. I'm gonna show you the steps here too. 3x cubed, I'll add x squared to both sides, right? And get rid of that quadratic term. And then we can subtract 2x from both sides as well to get a cubic to solve. And then we can factor to finish this off. 3x comes out, x squared minus 4. And then long story short, you get what it kind of looks like in the picture. 0, I think we would have suspected as an x value at an intersection point. And then this should have 2 other intersection points at positive or negative 2, the 2 things you can square and get 4. So I'll put that on the picture too. X equals negative 2, x equals 0, and then x equals 2 are going to be those 3 x values where the graphs cross. Okay, so we said this one's more involved. We're not going to try too many problems today because these problems are intense. They take a lot with this setup. So let's split this into 2 parts. Let's say area equals, maybe in the beginning, just this lavender shaded region has f of x bounding the region from the top. So what x values are we traveling from negative 2 to 0? So I'll use an integral from negative 2 to 0 to calculate this area. It looks like the cubic function is bounding the region from the top. So we'll put top function coming first. And the quadratic function is bounding the region from the bottom. So let's put that in careful parentheses. We want to subtract both of these terms, minus negative x squared plus 2x. close the parentheses, we're integrating with respect to x, so we'll put that dx at the end. Okay, that's half of it. Plus, we've got more area to add. Where did we leave off the last integral? We left off at 0, so we'll pick it up at 0. Can you take it all the way to the last intersection point? We'll take it all the way to 2. And then this time, your top function is that negative x squared plus 2x. And more importantly, put inside of parentheses, we could subtract all 3 terms of that bottom function. So 3x cubed minus x squared minus 10x with respect to x. So phew, this is most of the battle, just your setup. The beauty of this, even though this will take a while to simplify and integrate and plug in, the beauty of this is your setup is complete. Now we just practice with the integration and the simplifying. So again, feel free to stop and pause at any point and just try some of the simplifying on your own. We have negative signs to distribute, right? We want to combine the like terms. So your first integral goes negative 2 to 0. Let me try to do some of this simplifying in my head. So we've got 3x cubed. I'll definitely write that. You have minus x squared, and then just like with the intersection points, when that in that calculation the x squared's canceled, this is going to be plus x squared, so no quadratic term. And then here's your minus 10x, and minus, because of distributing, another 2x gives you minus 12x before closing off that integrand. Second integral, let's see, we've got more distributing to do, so it's integral from 0 to 2. This negative sign is going to go to all 3 parts, so maybe I just real quick right below this, let me simplify those 3 terms. You have minus 3x cubed plus x squared and then plus 10x to close off this and that. So I see, what do I see? Minus 3x cubed, I'll write that first. The x squared's adding to 0, right? Plus x squared minus x squared. And then plus 10x plus another 2x gives you positive 12x for that second expression. Okay, we are almost home free. We've got to integrate. So I'm going to drop the integral sign, take this up a power, make it 3x to the 4th, right, over 4. And then minus x squared, right? This will go up a power x squared, and the 12 will be over 2. So you'll get a 6 out front. And this is evaluated from negative 2 to 0. Plus, we'll get a very similar expression, I think just opposite signs for the second integral. This is negative 3x to the 4th over 4. And this should be plus half of 12, so 6x squared, evaluated from 0 to 2. And with this last little bit of space, we'll try the plug-in, right? 0 gets plugged in first in this first expression. So you'll just get 0 minus 0 for starters. And we want to subtract negative 2 being plugged in for x. This is 3/4. If I raise a negative to the 4th, I'm still going to get a positive value. Negative 2 to the 4th should give me 16, right? And then likewise, minus 6, if I take negative 2 and square it, I'll get times 4 for that first integral. Okay, last but not least, let's plug in 2 to the second integral. This will be negative 3/4 times 2 to the 4th, so negative 3/4 times that 16 again. And then plus 6 times 2 squared, so plus 6 times 4, and then I think minus 0 and 0 again. All right, and then getting our answer, area equals 3/4 of 16, so just 12. This is negative 12 minus 24, and we're adding, this should be negative 12 plus 24 to see what we get for a total area of those 2 shaded regions. Negative 12, and you're adding that, I think, to positive 12. This should be 24 square units of area bounded between these 2 curves. Double the work because you had 2 integrals to set up instead of 1. I put a unit circle here to help us out. Let's talk about a problem that involves some trigonometry. So imagine same setup. We kind of just want to get a sense of, do these functions crisscross? They should, sine and cosine, and which is the top and which is the bottom, region in question, function in question. So we'll graph sine of x first. We can use technology to help us out. Sine of x is going to come up from the origin and kind of like hit the x-axis at 0 and pi. This would be y equals sine of x. Whereas cosine of x, right, if I started with the cosine of 0, that puts me up at 1. It's going to come down through sine. They crisscross. It'll go down to negative 1 once you hit pi. So this is y equals cosine of x. And somebody gave us the limits of integration, so they just want the area bounded from x equals 0 to x equals pi over 2. X equals 0 is here, right? Pi over 2 should be right in the middle between 0 and pi. This should be pi over 2. So I see two bounded regions, one right here and another one right here. Go from 0 to pi over 2. So again, we're in the same scenario where you can't always call sine the top function and you can't always call it the bottom function. We need to split this up into two. So we need, what do we need? We need this intersection point. We need to know exactly where they cross. By symmetry, this should happen at pi over 4. It should happen exactly halfway between 0 and pi over 2. We can confirm that by using algebra, intersection point. The same way we did it in the first example. So we can set sine of x equal to cosine of x. And we can think about where that would happen. Where would those two things be the same? Let me look at this unit circle. I have to find a spot or two on this unit circle where the sine of x is going to equal the cosine of x. And if we think back to what we know about trig, we know that's when the x and the y are the same exact value. I don't see it happening in quadrant 1 except for this point right here. I see it happening where the x and the y are the same at pi over 4. Could you actually find in another quadrant where the x and the y are exactly the same? I feel like it doesn't happen again until over here where they're both negative at 5 pi over 4. So if I look at our picture, the one we care about is the one we suspected. This happens at x equals pi over 4, exactly midway in between 0 and pi over 2. And that should just help with a little bit of our setup. All right, now the exciting part, let's write the integrals. So our first integral starts where? It starts at 0, area equals, it goes to the first intersection point at pi over 4. Now we got to decide, are we going to set this up as sine minus cosine or cosine minus sine? If I look at the picture, for starters, the red curve is bounding the region from the top, and that's cosine of x. We're going to start our integral as cosine of x minus sine of x. Dx, and this is your top function. I'll put t for top, and this is your bottom function, b for the bottom. Then they crisscross, right? We'll say plus, let's do a second integral. Start at pi over 4, go all the way to where we want this region to end, right, at pi over 2, pi over 2. And what's the other small switch? Well, we've switched the top and the bottom function. Now sine of x, right, is bounding this second region from the top, and cosine from the bottom, dx. So that's your setup. Now we have to integrate, right? We'll go to our next line, and we've got area equals integral of cosine. That should just be sine of x. Integral of sine is going to be negative cosine. Because we're subtracting a negative, let's make this plus cosine of x. And this is evaluated from 0 to pi over 4. Second integral, let's see, integral of sine, we mentioned it, it's negative cosine of x. Integral of regular cosine would be sine, but we're subtracting, so minus sine of x, evaluated from pi over 4 to pi over 2. Now the plug-in, and I'll use the unit circle when I need to, so area equals, let's plug in pi over 4 first, so sine of pi over 4, plus cosine of pi over 4. Minus, here goes 0 plugged in, so minus sine of 0 plus cosine of 0. I like the second part of this to be in parentheses, just as a reminder that that negative sign gets distributed, if that's going to matter. Next up, I'll go to the second integral. We got to plug in the top number, pi over 2. So plus negative cosine of pi over 2 minus sine of pi over 2. And then minus what we get when we plug in the bottom number. So minus negative cosine of pi over 4 minus sine of pi over 4. Okay? And here goes the plug-in. This is sine of pi over 4. Refer to a unit circle if you need to check. Sine of pi over 4 is just root 2 over 2. Cosine of pi over 4 actually also happens to be root 2 over 2 in its exact form. And then minus sine of 0, right? I'll go to 0 and get the y value. Should just be nothing, should be 0. And the cosine of 0 should be 1. So we've got minus 0 plus 1. Plus negative cosine of pi over 2. So negative, I'll go to pi over 2. The cosine is your x value, should be 0. and then minus sine of pi over 2. So go back up here, sine is going to be 1. So minus 1. And last part, minus negative cosine of pi over 4, so negative root 2 over 2, minus root 2 over 2 again, the sine of pi over 4. And I'm sure some of these terms will combine. If we add these two together, we just get a square root of 2, half of it plus another half of it, minus 1, plus negative 1, so minus 1 again. And then minus, this should just be negative root 2. So you're really just adding another square root of 2. So in its exact form, you get two of these added together. You get 2 root 2 minus 1 again. Here's your exact area of those two regions added up. You always could give me a rounded decimal as well. You type that into the calculator, you get about 0.828 square units. That was it. I wanted to work on that for practice. Another thing I wanted to mention that some of you may have figured out back with this picture is there is a shortcut for this. Because of the beautiful symmetry of sine and cosine, we know these two bounded regions have the exact same area. So if we wanted to cut this work in half and just take one integral, I just wanted to give you this as an option, we could take just the integral from 0 to pi over 4 of what would be top minus bottom cosine minus sine. And maybe you'd suspect this, we could just double it. We could double this answer, get the same exact solution because we know those